So let's get started. So for the week 7, what we're trying to cover here is graph theory. So it actually have a lot of usage for graph theory, and just because a lot of models, a lot of mathematical problems can be modeled as graph theory, as graphs. And then, for example, social networks. You can use graph theory to analyze social networks, number of degrees of connection, and you can do clustering in the graph, try to understand the relationship between each individual nodes, and then understand the relationship between individuals in a graph. And then some other questions such as logistics problems in classic supply chain type of example, you need to understand how the transportation network should be and how would the transportation network should work. And then even in classic simple problems such as traffic lights and among different intersections, how could we analyze the coordination of the signals. All of these types of examples can be solved by graph theory. So what we're trying to do here is we're going to give you some tips on what would be a graph and how to describe the graph, and what type of graph models that we can use, and then how to use graph models to solve actual problems, and then why graph models is very closely related to math programming problems. Okay, so first of all, just give you an example that is how to use graph to model math problems. And then we want to understand the connections between graphs and math programming as well. So let's look at the first example here. Graphs as models really started with this example. So back a long time back, this guy Königsberg comes up with this problem that is seven bridges example. So he was saying that if I have a bridge that's connecting different segments of the city, for example, segment A and segment D is connected by bridge E, and then segment B and segment D is connected by bridge F, and then area A and area B are connected by two bridges. One of them is A, the other one is B. Not capitalized. Capitalized is using to represent the area, and then smaller sized letter is used to represent the bridge. So in this case, how can we represent this graph as this problem as a graph? And then if you look at the bottom chart on this page, you can see that if we use a node, and then usually in a graph context, we also call it as vertex. So in this case, if we use node or vertex A, B, C, D, capitalized A, B, C, D, to represent the area that we show in this chart, then show in the above graph in that map, then and then we would use edges or connections between A and B using small letter A and B to connect those nodes. Then we also call these links as something, especially in graph, we call it as edges. Then we could represent the above relationship among the areas and also the bridges to represent, using this graph to represent that map, right? So that's really the start with the graph theory. Königsberg started with this problem and then started to analyzing using this graph that's analyze the map. So let's look at so this is clear by looking at this bottom graph, right? Okay, now let's think about one classic example of using graph coloring. So this is like in the United States, all of these 48 states, they're connected, but here we are asking you a question: is it possible to color all the states with 4 different colors, so that any 2 regions that share a common border meaning that a flanks of any 2 regions that share a common border are assigned different colors. So meaning that if they share a common border, then their distance length is greater than 0, which is really 1 in this case, right? So in that case, question is it possible that we pick 4 colors and then you would be able to color the whole map? So let me find a pointer. So in this case, for example, if Maine is labeled as red, and then this state, Vermont, New Hampshire probably, right? New Hampshire shouldn't be red in that case, right? So that's the idea. So and then the answer for this problem is really this: if we use different shape here to represent a different color, and then you would realize one of this solution would be this, right? This is something we would call it as feasible solution. So when you did linear programming, we talk about feasible solution, optimal solution. And then in this case, we don't know which ones, we don't really have an objective function, right? But we would be able to find a feasible solution in the sense that as long as we're able to meet that constraint that the neighboring states will not share the same color. So in this case, if you look at all of this, right, California, Washington State, and all of this, all the neighboring states are using a different color. So you use 4 different types of colors here, like different shapes, triangle, square, circle, and a star. You would be able to color the whole graph, color the map, United States map. So this is one of the application. Of course, here we didn't really dig into detail on what type of how did we solve this problem, but really just give you a sense on what it is, a graph model, and how potentially we can use it. And then, as I actually just mentioned, you could describe a graph using multiple terms. That's actually that's unique to graph theory. So one of them is called vertex set. So all the nodes are considered to be the vertex set, and then all the links are considered to be edges or edge set. And then there are some other key terms that you should remember. One of them is called incident. So incident is really talking about what is incident to a specific node. Then all the edges that's incident to the edge. So for example, if we go back to this example, the incident of A is really AB, edge AB, CD, and E, right? And then the incident of node D would be edge E, F, G, okay? And then of course here we talk about another different term that is adjacent. So adjacent is really that would be 2 things, right? One thing would be and also adjacent. One thing would be nodes, a relationship between A and C. In this case, we see that A is adjacent to C node-wise. Node A, capitalized A, is adjacent to node C. That is one term that we talk about sometimes. But of course, in other words, you can also talk about adjacency of edges. In this case, E and F would be adjacent to each other in terms of the edge. But majority of the time, we don't talk about edge adjacency. Majority of the time, we talk about only the node adjacency. Of course, also the incidence. I think sometimes we even have the incident of edge. For example, edge E incident to node A and D. Okay, so there's one more here, this number of degrees. It's nothing but how many edges that connect to a specific node. Okay, and then in this case, for example, degree of node A, capitalized A, would be 5 because it has edge A, B, C, D, and E. That's actually connecting somewhere, and then that would be considered as degree for a specific node. And then sometimes we also talk about how many degrees of connection between B and C, capitalized B and C for those two nodes. It's 2 degrees of connection because you need to use 2 edges to hop from node B to node C. That is another term that we use in the graph context. Okay, so and then here actually in the third section we switched gear a little bit. We say, okay, how can we use graph to do some models? In this case, for example, we can fit a piecewise linear function to data. So piecewise linear usually we refer to a specific set of multiple linear functions to fit the data. For example, in this case, you could fit one line here and second line there. Then it will be considered as piecewise linear function. And then in this example I just showed, it actually have 2 pieces in the piecewise linear function. And then let's look at this possible solutions. The first solution on the left, you see that is a linear line, and the second one in the middle apparently has a piecewise linear function, but it's trying to connect every single node to fit a model, right? And then the third one on the right is really 3 pieces of piecewise linear function there. Just want to point out that you probably already studied in computational mathematics course in the middle. Apparently the approach in the middle, the graph in the middle, if you're really trying to fit a model like the one in the middle, it would be considered to be overfitting, right? And then potentially 1 or 3 would be the possible solutions if you are trying to fit the model to the data. Okay, so now now we want to use a different example here. For example, if we use this graph on the top, we could potentially first of all, we would be able to come up with something called directed graph. So in many of the graph theory, usually it stands for usually there is a assumption for some of the type of algorithms or methodologies. It has a assumption that is called DAG, which is something called directed acyclic graph. So that is to say that the graph is directed, meaning that in this example, there is a direction between 1 to 2, but 2 is not pointing to 1. So that is directed. Acyclic, meaning that there is no cycle in the graph. If you look at the first example on the top, so far I don't see any cycle at all. So because you can see if you start from 1, you go to 2, 2 goes to 3, but 3 doesn't come back to 1. If 3 comes back to 1, then it's a cycle there, right? So sometimes we use directed acyclic graph to be the pre-assumption for many of the algorithms. So just pay attention to whether the model actually have a cycle. I mean, whether the graph actually has a cycle. That's one. And second point that I want to bring up here is that here first of all you see the direction. Second possibility here is there is a cost associated with all the nodes. So as simple as when you travel, from node 1 to 2, it takes 2 minutes, but from 2 to 3 it could take 5 minutes, and then from 1 to 3 potentially it could take 10 minutes, for example. That would be a cost. So the cost could be time, could be money, could be anything. So it's when you model the problem, you can have certain costs embedded into the network structure or embedded in the graph. So so that's why you would immediately realize that it could come handy in modeling the road networks. It would be handy to model the communication networks. It would be handy to model social networks. And then you would be able to analyze the graph in a much more detailed manner. Okay. So and then the chart on the bottom, it really doesn't give too much information there, but the idea, I believe it was that still, if you have a cost involved, potentially a solution could be different from without a cost between nodes. Okay, so now let's move on to next example. So this example is some classic example is called matching. And then matching is saying that, assume that we have all of these baseball players, Al, Bo, Cher, Doug, Ella, etc. That's all the players. And then potentially they could play different positions. For example, Al can only play position 2 and 8. And then Bo can play position 1, 5, 7. And then what we do is if we use the players on the left-hand side, and then use all the nodes to represent all of these players. On the other end, on the right, if we use all the point to represent the positions, as you can see here, it's the position 1 to 11, and then you have all the players A all the way to Paul, which is P here, stands for Paul. So, and then if you look at the edge that we designed here on this graph, because Al can play position 2 and 8, you can see that A is connected to 2 and 8 on the right, and then B can play 1, 5, 7. That's why B is connected to point 1, point 5, and point 8, point 7, right? So now the question becomes, with this mix, with this possibility, would you be able to find a match? Would you be able to, if you are a coach, would you be able to find a feasible solution for your, if you have 11 positions to fill, and then if you know that even though Bo can play position 1, 5, 7, maybe he plays position 1 much better than 5 and 7, then in that case you can have a cost structure embedded between B to 1, B to 5, B to 7, so that when you're trying to match, find a match or find an assignment of the position to the assignment of the players to the positions, then you would be able to find the least cost matching, right? Even if you don't have a cost structure in the network, you can still find a match in this. In other words, you can still find a feasible solution for this matching problem. To make it a little bit more complicated, then you would embed certain cost structure, as I just mentioned, if Bo is really doing better on position 1, then we can use B21, use a smaller number to represent that he's very good at there. So if we're trying to minimize the overall cost, and also with certain constraints such as each position has to be played by someone of all these players, then you would be able to find a minimum cost solution for this problem. Okay, so just to give you a sense there, but this really is one of the examples and one of a classic problem that we usually come up. I mean, you would come across. So so I'm actually here. I didn't really try to explain to you how we can solve this problem, but in the textbook it has a lot of information on this. What really is more important is when you have a problem in hand, the business problem in hand, how would you be able to translate that problem into a matching problem? That's probably more important aspect you should pay attention, and potentially that could be very handy and useful. Okay, so let's look at a different example. In this example, that is to say that suppose that certain it's called policing a city, and then it's also called a vertex covering problem. Suppose that you want to find so let me actually show you what is the vertex covering problem. We actually we could, two possibilities. We could go to the textbook, or instead let's go here. I'll explain to you what is a vertex cover problem from here. So the vertex cover problem is to say that in a graph that is represented by all the vertices and all the edges, and then we're saying that select a subset of the node so that each edge is covered on a graph. So in other words, if you look at this graph here, you can see that if I select all those three nodes, red nodes, every single edge on the graph is incident to one of those nodes, right? Because see here, this edge is covered by this red one, and this edge is even covered by two nodes, and then this edge is covered by this node, and then this edge is by this node, this edge is covered by both of those two nodes, and then this edge is covered by the red node as well. Okay, so and quickly you would realize the one on the right hand side also is covered by other nodes as well. And the next question is, would you be able to find a minimum vertex cover? That is, to find a minimum set of nodes that will be able to cover all the edges. And then the same problem as what we saw for the first one on the top left, you can see that the new 2 points that you can find are really the twos in the middle for the first problem. All the edges are covered in this case. And then also for the second example on the right, you need the 3 in the middle to cover all the edges. And then, of course, graphically it looks simple, looks straightforward. However, mathematically, if you have a much bigger set of nodes, it's much harder to solve, right? So let's look at how this problem is modeled. So here it says, okay, minimize the total cost. That is to say that if we look at before we look at the objective function, let's look at the first constraint. The first constraint says xu plus xv larger than equal to 1. That is to say that x is really xv is whether the specific vertex is in the minimum vertex set. Okay, so now if we're saying that, okay, xu plus xv is larger than or equal to 1, that is when u and v are two different vertex, and then u and v together connected this edge that is connecting each other, so that you don't really need both of them to be selected, because you only need to select one of them, you would be able to cover both, right? So that's why xu plus xv should be at least covered by one of them, so it's larger than or equal to 1. And then on the other second set of constraint there says xv is either 0 or 1. So meaning that, and this xv is really generic, right? Any of the node can be xv. So here saying that you can only pick, you can either pick this node or you don't pick that node. That's why xv would belong to 0 or 1. And then now it's simpler. So if you pick certain nodes, then there's a certain cost associated with picking a specific node. Then you have a CV, which is in the objective function. Then you use that cost times whether xv is picked, and you sum all of them together. You're trying to minimize that. And then, of course, if you don't really have a cost associated to pick a specific node, then you don't have that CV in front of the xv. Then you purely just minimize sum of xv with those two sets of constraints, and then you will be able to solve this problem, right? So as you can see on the top, before we look at the formulation, it says, assuming that there's associated cost of CV larger than or equal to 0, then this is a weighted minimum vertex cover problem. So without this CV, it's really just the minimum vertex covering problem. And then just want to point out, looks simple, right? It still kind of look like a linear program. Remember that last time we studied linear program, except there is one difference here. We said xv can only be 0 or 1. In other words, it is binary, and then it can only take integer values. Not only it can only take integer values, but also it can only take 0 or 1. That's why this type of problem is called integer linear program, or in other words, in this specific example, it's really binary linear program. And then it has certain features that's unique to this type of problems. That's why you don't really use simplex method to solve it. You have to use special tricks to solve the integer linear program, which is something that we're going to cover probably in a couple of weeks. But hopefully, at least for now, you know this set of problem is unique. It's not just purely a linear program. Okay, so now this set of problem is there, and then if we go back to the example that we have, that is really here one of the example here says if we need to find a set of nodes, and then these nodes would be able to policing different cities, and then which would be the right node, and then it is a vertex covering problem. Okay, and then we want to quickly go through this shortest path problem. So that is to see how would you be able to find a shortest path between two nodes on a graph in a systematic way to quickly to solve that problem. So as you can see here, the algorithm is called the Dijkstra algorithm, and then it is on the page 324, and then I hope you can read that problem on your own. It's actually straightforward in the sense that it's very organized way to solve the minimum path, a shortest distance path problem. Of course, there's a lot of other extensions of this algorithm, something called k-shortest path problem. So instead of finding the shortest path, is it possible to find the 5 shortest paths? Meaning that not the 5 shortest, but really the 5th, the 4th, or all the way to the shortest, and then the next to the shortest, least to the shortest, etc., etc. So that you will be able to find a k-shortest path. It's just another family of a problem. Okay, so and then we actually cover the maximum flow problem. So maximum flow problem is another set of problem that is to say that for directed graph, that is with this set of V and all the edges A with a source vertex S and a sink vertex T and the finite capacity of Uij for each arc between I and J. And then if two of the nodes are not connected between I and J, that is Ij doesn't belong to A is a set of edges, then the Uij is 0, saying that the capacity between the nodes that are not connected is virtually 0. Okay, then the question is, how do you find a maximum flow from S to T in the graph? And then the solution that you go through is like the following. Step 0 is set the current flow to 0, FC to 0, and then find a direct path from S to T in the current graph if there is no such a path stopped. And then the maximum flow from S to T is really FC, which is 0. And then the next step is compute the U-minimum, the minimum capacity in the current graph of all the arcs in directed path. And then for each of the arc in the directed path, update the residual capacity in the current path. So essentially, it's trying to this just purely just trying to update the capacity of each path as you go along, and then at the end you would be able to find your maximum flow. And apparently, I'm not really going through this example too much detail at the moment. Only one of the key reasons is because I really just want to introduce you to the K graph types of problems that it can solve, so that you solution methodologies there majority of the time those methodology off-shelf computation packages already included them. And then the question is how it's more important how you can model the problem to this type of problem so that you will be able to solve it rather easily. So in other words, modeling itself is more complicated than solving the problem. And then here it says, okay, potentially one of the example is bipartite matching problem that we introduced earlier in the example that I proposed earlier for the baseball players. If you don't have S and T, ignore what we have here on this chart. So on this graph, ignore this portion and also ignore the portion on the right hand side. So in this case, x1, x2, x3, x4 could be the baseball players, and then y1, y2, y3, y4, y5, y6 could be the positions that we talked about, right? And then potentially you could solve the matching problem by a maximum flow problem. What you do is you start from S. You can come up with two pseudo-nodes. Pseudo meaning it's not real, right? You put them in. One of them is S as a starting point, and T as a termination point. Sometimes we also call it origin and destination. And then you mark the capacity among the S to each of the players on the left hand side, and use one edge or arc link to connect them, and the capacity is 1. And then on the right hand side, you use all the positions to connect to the destination, and then give a capacity of 1. If you are able to solve the maximum flow problem on this graph, you would be able to find the match, would be able to solve the matching problem. Earlier I talked about that we could use a cost associated between the players, and then it could be a minimization problem. Of course, if you design a cost structure a little bit different, then it would become a maximum flow problem. You would be able to solve it using maximum flow and solve the matching problem. Okay. So now we really want to go through this example, which is something it's really a hard problem. This one is traveling salesman problem. So as you know, UPS driver starting from, suppose the UPS is in location A, and then he needs to travel. He need to have the other cities that he has 5 packages that he needs to deliver. That's B, C, D, and E. Of course, there is a cost associated with starting from point A. If I go to B, the cost is 1, and then starting from A go to C, the cost is 9, and then starting from A going to E, the cost is 3. So the question is, how can I find the best tool for the UPS driver starting in the morning? He would be able to visit all the locations B, C, D, E, and then come back to A, and then with minimized cost. And then in this example, you can see that the tour that he should make is from A to D, which is 3, cost is 3, and then from D to C, cost is 4, that's 7, and then from C to B, cost is 2, so that total cost is 9, and then from B to E, cost is 5, so total cost would be 14 now, and then going back from E to A, 14 plus 3, as total cost is 17. So now the question is, how would you be able to solve this problem? Okay, so now actually I want to go back. Let's go back to, really want to go here and then look at as you can see here, you have multiple solvers and different algorithms. They can be solved in Python, in R, in C++, in Java. So it's all embedded in many places. But it's really the key thing is to understand what is it. And then in this example, here you can see one of the solutions. There is one of the solution for this example. We already talked about the idea there. I want to give you a heads up on what would be the formulation of this. So here, if you look at this set of math program, so traveler salesman problem literally is this formulation. So I want to quickly give you some tips on what is it. So let's look at this formulation. So suppose that we define the decision variable as xij. The path goes from city I to city j if there's you decided to select this between I and j, that's edge. Then xij is 1. Otherwise, if you don't really select that path, you really don't select the node, the edge between node I and node j, then xij is 0. So now if you look at the overall cost, if the cost between between I and j, look at the objective function, if the cost between I and j is Cij, then what we're trying to do is you're starting from I equal to 1 and visit all the nodes j which is not I, and then j starting from 1. So meaning that starting from all the nodes other than 1, and then you visit all of them, sum them together using Cij times Xij, and sum of them together, trying to minimize that cost. So that is a straightforward, right? Its objective function is trying to minimize this total cost. And then next question, let's look at the constraint. The first constraint is really tell you that Xij is between 0 and 1, meaning that in this, apparently there is a reason that we picked between 0 and 1. Of course, ideally it's really between either 0 or 1, right? Now it's between 0 or 1. There's a reason only because this formulation is easier to be solved than the solution then if it's really a binary problem. Okay, so that makes sense. You can use that notation, that constraint. And then let's look at, let's skip the second constraint and look at the third constraint. The third constraint says, starting from node 1, for the rest of the ij, all the xij, for each one of them has to be selected. Meaning that if you go from 1 to, because you don't come back, right? You have to visit all of them. Yes, you will come back, but you can only come back as the last after you visit the last node. So when you go out, when you are starting from node 1, going to other places, any one of those places, you can only go to one of them. That's why starting from 1, go to the other places is constraint. The third constraint tells you sum of xij should be 1. You can only visit one point or one node and you don't come back right away. That's that constraint. If you look at the next one, that is say that if j is 1 and then j is not I, sum of them, meaning that at the last stop, you can only come back once, right? In the example, at the end, you have to visit back to point A, node A. So that's that constraint. And then let's look at the last one. Last one is really something we call it as the subtool, avoiding subtool constraint. So what is UI? UI is a dummy variable, and then this says that you would not, you are trying to avoid subtools in your visit. What is a subtool? That essentially says, we said that we can visit all of them, but potentially if you don't have that subtool example, you could end up with visit B and then visit E and then come back to A again, even though you haven't visited all of them yet, but potentially that could be the solution. So in order to avoid that situation to happen, this is called avoiding the subtool type of constraint. it's much more difficult to understand conceptually at the moment. You can read this if you're interested in not only here but also in the textbook has some explanation as well. So now here just give you an example on how that problem can be solved. As you can see, it's no longer as simple as what we saw earlier, and it takes a lot of iterations to come up with a final solution on the right hand side, with the optimum distance being 249 in one of the examples that we have. And then this here is another example. If for a TSP problem, if you have 40 to 60 cities, it take you around, say, a lot of iterations to come up with an optimum solution to find the minimum distance. Minimum cost in this case is minimum distance. And then it has many other ways to solve this problem, but one thing that you should realize is really definitely not a easy problem to solve, and we categorize them as an NP-hard problem. Okay. Now, next thing that we want to go through is really what we already discussed earlier. For example, this is a vertex cover problem. It's really a math programming. It is as simple as this representation. And then maximum flow, trying to maximize that flow, meanwhile subject to certain constraint. The first set is really tell us something called conservation of flow. So the idea is anything coming out of I going to some other locations, some other nodes J, all of the flow going to J should be equal to other flow going out from J, because you have to travel, right? So there's no loss. There's no information loss that happen in the node. So that's why this is called conservation of flow. And then second one says that the flow on a specific edge should be less than or equal to the capacity, Uij. And then Xij should be less than or equal to 0, of course. And then we're trying to maximize all the flow, so that maximum flow on the objective function. And then here, this is really concludes what we planning to cover for the graph. And then here is the problem. Homework. Okay. So now, because today we actually kind of started a little bit late. So let me see. Let me find the slide set, and then to decide on what should we do. Okay, this set is really next section in week 8. It's really reasonably simple. So let's quickly go through this, hopefully in a couple of minutes, 5 to 10 minutes. So so in this section, we switched gears to something a little bit different from what we discussed in the past 2 weeks. One of them is previously we discussed linear programming, we discussed graph theory, and the graph is part of linear programming type of problem. But here we switch gears, we say, okay, let's look at something else. That's something called decision theory. And then first of all, you have to understand what is the probability and what is the expected value, assume all of you already know. And the second thing is what is decision trees, and then what would be the sequential decisions and conditional probabilities, and then what type of decision you can make under alternative criteria. And then nothing but suppose that you have a decision to make, because you know that if you are venture capital, you want to or you're a private equity firm and then you want to make a decision on which investment that you should be making on different various selections of projects, then you know that the success of each project down the road under certain different conditions would be different. So of course, there is a success probability under certain conditions or certain paths of how it's going to evolve down the road in the next 5 years. Then you would be able to make that decision using this methodology, something called decision tree. And then, of course, it has two types of decisions. One type is deterministic. The other type is chance or risk, stochastic. Most of the time, we're talking about stochastic type of decisions. Okay, so now what is a chance? Chance is really that a probability. Suppose that a game has outcomes of A1 all the way to AN, and then each one with a payoff of W1 all the way to WN with a certain probability as is P1 all the way to Pn with a summation of all the probability being 1. And then each one of the probabilities between 0 and 1. And then the expected value of the game is as simple as W1 times P1, which is the probability of the first outcome times the payoff of the first outcome plus W2 times P2. Here there's a typo actually on the textbook. This is W2, which is the payoff of the second scenario times the probability of the second outcome plus etc. should be Wn times Pn. That gives you the expected value of the game. It is really a weighted average based on the probability. And then you can do some sensitivity analysis based on your output and then see how sensitive your payoff is if you kind of shock different scenarios. Okay, so what is a decision tree? Decision tree is really that in this example, you think about, okay, I have something, maybe a house. I want to think about, okay, should I tear it down and do a new construction, or should I just remodel? In this example, it's really not a house. I think the textbook is using an example of I believe I couldn't remember on top of my head, but really the idea is the same, right? Suppose it's a house, and then you can make a decision, say, okay, if I do a new construction, after new construction, there's a probability of certain things. What if the project didn't go well? There's a successful probability of 0.2, and there's an unsuccessful probability of 0.8. That actually, in this house example, it probably doesn't make sense. The successful rate should be much higher than unsuccessful, but that gives you an idea on what we're trying to do, we're trying to model, right? And then says, okay, what about in the remodel scenario? It could have two probabilities as well, one probability being successful, second one being unsuccessful. Suppose that we have a payoff that is associated with each one of these paths. Suppose that there is a corresponding payoff of this path, and then the second path, meaning this one, and then there is a success in this payoff for this outcome, and then there's a payoff for this outcome. So now you would be able to find if you use maximum expected value to make a decision on whether you should do the new construction or remodel, then you would be able to, based on the maximum expected value, to make that decision, right? Okay, now just want to let you know that introduce you to concept that is, number one, in this tree, there are different branches, and then each branch has an associated probability and also has a certain payoff. That's number one. Number two, you should realize there are two types of nodes here. One node is using a square. This node is called a decision node. And then the other one is a circle it is something called a probability node. So you can see that in this example, it's clear on the top, if it's a circle, there's a probability of success and a probability of unsuccess. And then on the bottom, same thing, there's a probability node, but at the beginning, there's a decision that you can make in this example. Okay, so with that introduction, if you look at this example, now things become a little bit more interesting. So there's a sequential decisions and there's some certain conditional probabilities. You can see that spin is trying to spin something. I don't know. I read the textbook, and at the moment, I probably wouldn't remember exactly what that is. It looks like if we look from the bottom up from the end here, so we're saying that if you spin and then you can take $6 with a certain probability, and then if you spin, so the decision is really whether you would spin or you stop. In certain case, if you look at this decision node, says, okay, go to spin 3 or take $4. So that's a decision node. And then in this probability node, you can see that 4 probabilities, each probability have a certain payoff, and then what is the expected value? In this case, the expected value would be 0.25 times 10 plus 0.25 times 6 plus 0.25 times 4 plus 0.25 times 0, and then its expected value is 5. And then in this case, if you go back one step, you say, okay, if I know the next node has an expected value of 5, of course, I would go to spin 3 instead of taking out $4, right? And then similarly, if you go all the way to the beginning, what would be the expected value for the first spin? Okay, I think this is clear. If you look at this node, either take $6 or go to spin 3, and then you can realize you would take 6 instead go to spin 3, right? So usually what you do is going from the end of the tree all the way back to the beginning of the node, you would be able to find the expected value for this decision. So that is a decision tree. And then, of course, there's some case studies in the textbook talk about decisions under using alternative criteria. How would you make a decision on new construction or remodel, as we discussed, and then how do you investment or just don't do anything, just naturally to one of the example there. And then one more example is regarding investment strategy. How would you make a decision on what type of investment you should take you should make at certain stages? Now that's pretty much everything that we plan to cover, and this is a homework for chapter 7, which is week 8. Do you have any questions? Okay, so if not, we'll just stop here. And then please feel free to reach out if you have any questions. Send me an email, and then we would be able to answer. I will be able to answer the questions. Okay, thank you and good night.